We come now to the last, not least, presentation, invited talk from Pascal Vivet on 3D-IC advanced technologies for smart images. Pascal Vivet is Scientific Director of the Digital Systems and Integrated Circuits Division in CEA-LIST, Grenoble, France. He received his PhD from Grenoble Polytechnical Institute in 2001, designing an asynchronous microprocessor. After 4 years within STM Microelectronics, he joined CEA-LIST in 2003 in the Digital Design Lab. His research interest covers wide aspects of circuit and system-level design, ranging from system integration, multi-core architecture, network-on-chip, energy-efficient design, related CAD, design aspects, and in strong links with advanced technologies such as 3D integration, non-volatile memories, photonics. He was project leader on 3D circuit design and integration since 2011. He participates to various TPCs such as Async, Date, 3D-IC, ISPLET conferences. He served as a member of the organizing committee of the 3D workshop series at Date from 2013 to 2015. And maybe you accuse me, I can tell that we were organizing also a 2022 workshop at Date. And to the D4-3D workshops since 2011, and to the 3D-IC conference. He has authored and co-authored more than 120 papers and holds several patents in the field of digital design. He is a member of IEEE. So please share your screen, Pascal. Pascal? Okay.
Oh yes, I'm sorry, I was off. Can you hear me now?
Yes, we have seen
good.
your first slide, but we did not see you. So
okay, sure. Can you see me now?
Yes.
Yes. So hello, Peter. Many thanks for the introduction, and many thanks, Paul, for inviting me to participate to the 3D-IC conference. So it's really my pleasure to be here with you today. Of course, I would really be physically present in Raleigh, in North Carolina, with all of you people, but this is as it is as of today. So it's really my pleasure to give this talk for today. So the talk is going to talk about 3D-IC advanced technologies for smart images. So we are working on smart imaging, and this is the vision that we have and that I would like to present in a nutshell. So we are envisioning to prepare the next smart imaging systems, and a smart imager could be an edge AI device. So everybody is talking about edge AI, which is meaning how to have AI, artificial intelligence and machine learning onto our everyday pocket devices. And a smart imager could be part of that, meaning that we could bring AI within the imager itself. And I think that there was a very nice presentation just before by Red Davis, and I'm really glad about that. So such images could bring advanced monitoring capability. It should be power and event-driven with high frame rate, low latency, and embedded some computing, some AI processing and recognition capability. We are, of course, targeting many different applications. Smart sensors, smart monitoring, house devices for cyber physical system-like applications, but also high-end integrated image sensors for automotive applications. And if we are able to embed some smart and accelerators within the sensor, automotive applications would be much more powerful. But we are also targeting a low latency and reduced form factor, for instance, for AR and VR. All that should come with a common objective. The first one is privacy, because there would be no raw data transmitted to the cloud between the imager and the cloud. So this is a way to protect the data. But most of all, this is obviously to reduce energy, because instead of storing big frames output of the image sensor, we could directly compute and detect objects, visages, persons, cars, pedestrians, and everything within the sensor. And for that, we should be able to do that on raw data within the sensor without storing the image outside on a massive large memory such HBM onto a GPU which should be attached to the sensor. So after this introduction, I will talk on the different topics. So what are the current technologies for images, and what is the state of the art in this domain? Some example of what we have done in CEA, and then bring the vision about this 3-layer smart vision system. So let's start with the 3D available technologies for images. So here is a presentation from YOL, from a previous technical report from YOL from 2019, where we can see a very rapid evolution of images, starting from front-side images. So everybody has forgot about that nowadays, but with the first BSIs with one single layer BSIs and 2-layer BSIs, which were connected with TSVs, that was introduced by Sony in 2016. Then we had BSI with hybrid bonding, connecting the two wafers together to have direct connection between the image sensor and the pixel array and the logic below. And then we are moving towards a higher number of layers with, for instance, 3 layers as the last presented result from Sony that was in 2017 with the DRAM. But we have more things to come, and here is again the same thing where we can see more details with a pitch reduction. So we had the first 3D backside images introduced in 2016 with some very aggressive pitch at that time already. So Sony introduced in 2016 4 micrometer pitch between the two wafers of the pixel and the imager. At that time, ST and ourselves and in CA we were able to achieve an 8 micrometer pitch. And at that time, we were co-integrating the pixel array with the ADC on the bottom, with the logic on the side, as we can see here. Then progressively, in the years later on, we have increased the pitch to have a more aggressive pitch and to put more signals to be faster, and thanks to larger pixel array, to put some ESP, image signal processing capabilities within the logic device in the middle. So, for instance, in 2018, we have able to show a very aggressive pitch of 1.44 micrometer, and we'll show that later on in more details. Then we can see 2 different parallel tracks. The first one is we're going to have more layers. That means more layers because we want to have more memory in order to store the image buffers. So Sony has done that with DRAM and TSVs as a 3rd layer. They are envisioning to continue in that direction, but also using SRAM, and to have also some ESP and DSP for neural networks. And they have presented very recently at the last IECC conference this February in 2021, a DSP for CNN acceleration in a 2-layer imager. And in parallel of that, where there is more memory and more capability, we can see a second track where we are having more parallel connection between the pixel array, the pixel themselves, and the pixel acquisition, instead of having a direct connection pixel to the ADC on the bottom layer. And we have worked on that, and we'll present that in more details afterwards. And Sony is doing the same at pixel level. And there are also some work of using HD TSVs and monolithic 3D in order to continue further the co-integration of the pixel onto the device. Our target is to co-integrate 3 layers, which is pixel, logic, and an extension of memory. And this is what I'm going to present to you today. So how is done this hybrid bonding technology? I suppose that most of you know that. So the idea is to prepare two wafers. So we are doing wafer-to-wafer stacking for images, preparing 2 wafers with copper pads and hybrid bonding. So preparing and CMP and doing annealing after thermal annihilation. And using that, we are able to achieve a very nice surface, which is very solid, using a very fine pitch and high throughput in terms of process fabrication. And this is very well controlled today. There is lots of different equipments, and this is mature technology today into the industry. This is used for wafer to wafer, and we are also working in CA to apply that for die to wafer, for chiplet and high performance computing. But this is another topic that I will not present today. Such technology, hybrid bonding, has been used, for instance, by ourselves and our colleagues from ST Microelectronics in a BXI imager, 2-layer, 130 nanometer pixel array, full range 600 megapixel, and an hexa-core CPU for computer vision in the bottom. And we've been able to achieve a very high density 3D interconnect with a pitch of 1.44 micrometer. We can see here the cross section of the device that has been fabricated in our clean room capabilities in CA. And the device is fully functional and showing that we are able to do today, and the technology is mature in terms of industrial capability to achieve very aggressive pitch. So the question is, what can we do with this pitch in terms of architecture? Because we don't want to stay there. So people are now moving to have CNN accelerator. This is an example of what is doing Sony today. So we have, again, the same kind of thing with a pixel array, direct connection on the bottom, and to have a computer vision or CNN processor. One of the issues of all that is that we have really a bottleneck in terms of imager architecture, because we have a standalone pixel array, and then with serialization and with very fast ADC, we are converting with signals here. But everything is serialized, and then we are putting everything into memory and doing the processing afterwards. This is energy hungry because we need to first sequentialize, store, and process. And we are not taking the benefits of the high density connection, which is offered by the 3D stacking. Actually, the 3D stacking here is really limited on one part of the imager layout. So what we are proposing actually is to get rid of the data rates and all the control bottlenecks which are used today in terms of the state of the art, and to have a fully distributed and in-focal plane architecture. So the idea was to have distributed pixels and ADC array, distributing computing capability on the bottom, so that we can have direct connection between a group of pixels. Of course, this is not one single pixel, but a group of pixels with an SIMD PE engine that would be able to implement that. Thanks to this locality, this is very good also in terms of wake-up mechanism, dynamic range, exposure, because the exposure control can be done locally instead of globally. So that means that we can have much better exposure control. This is much flexible and scalable, because we can have a modular architecture with a graph and a group of pixels with the sizing of the PE engine on the bottom and the associated memory, so that we have a modular architecture. So the architecture looks like that. So we have a group of pixels with ADC, which are in the plane of the first layer, with processing, SIMD engine, and attached memory, which are communicating with our neighbors, north, east, south, west, from clusters to clusters. So we have implemented such an architecture a couple of years ago. So we have 2 layers, top layer with this pixel matrix. We have 1000 by 700 pixels. Bottom layer, which is a processor array of 3000 P engines with global controller, local instructions, and some memory. And all that has been implemented in a 130 nanometer technology, which is kind of old technology, but we were able to achieve on the circuit correct behavior and to do some measurement onto the circuit. And we have everywhere this distributed architecture. So here are some examples of what we have been able to implement onto this circuit, and proving some different application examples. So we are able to run some classical computer vision application, trajectory assistance, detection, measurements, but also some scene detection, pedestrian localization, motion vector estimation, and that kind of thing. But also not the least, some neural networks convolutional layers. So with the design as we have it today, we are not able to fit all the neural networks and the weight in terms of local memory. So we are able to only fit the first layers onto the Retin smart imager, and the remaining layers are implementing onto the host. So the circuit is functional, but we are limited in computing and memory capability, and this is why we want to introduce a 3rd layer. If you want to have more details, all that has been published in the IISW conference in 2019. There is another example of a smart imager. So this is totally a totally different example. Here, this is an ultra low power wake up imager. And this device is done for motion detection, auto exposure, and object recognition for smartphone. And the application of that is front side camera, so that the camera is recognizing yourself as a people and is waking up the system for ultra low power system behavior. So the idea is to have that kind of camera with very low resolution, of course, that is able to detect a person in the range of microwatts. So that is implemented using optimized finite state machine with multi-mode behavior. Mode 1 with 4-bit detection only. Then if something is started to be detected, we are increasing the accuracy with 6-bit detection. And then we are going to object recognition with a very lightweight recognition, which is based on XOR edge extraction, which is requiring a very small footprint. We can see here in the layout of the chip. This is a single layer chip with a very small pixel array here and the processing unit capability and the memory which is required to store the weights. So the chip has been implemented and measured in a C40 nanometer technology. And this is recognition of the image after the readout. This is very, very low quality, of course, but we are able to detect a person and showing that we are able to wake up the overall system that is integrating this smart imager. And all that is achieved in less than 1 to 2 microwatts, and that has been measured and published at a VLSI symposium in 2020. So this is an example to show that smart imager is of course achievable for specific recognition application. In that case, 3D integration would reduce the silicon footprint in order to further optimize the footprint of the device. So starting from these technologies and examples, so we are aiming to build a 3-layer smart vision system. And this is why we are doing that again. So the idea is to move from image generation to information extraction. And this is where we are working in the edge AI domain. So we need to shift between the compute and storage. We need to have enough storage capability on chip. This is a big challenge, of course. We need to be able to size the neural networks so that we are able to embed them on chip using 3 layers. And the 3rd layer will be used for computation capability extension, but also most of all for memory extension. We are also designing such an architecture that would be able to address multispectral management. So not onto a single device, but we are aiming to work with different partners so that the same kind of architecture template can fit a visible application with standard pixels from CMOS and visible CMOS, but also for infrared and using infrared pixel and post-processing. Of course, we are targeting lots of different applications as with all our partners, consumers, smart buildings, healthcare, industry, automotive, and so on. And we are studying various applications in order to size the problem and to see what we are able to fit onto such an architecture template. So here is the architecture proposal. So starting from the existing architecture that I presented in more detail just before, which is only 2 layers. So the idea would be to integrate a 3rd layer with more capability in terms of compute, but most of all memory. The 1st layer would be partitioned onto these 2 layers with pixel array and the distributed ADC in the 2nd layer. The compute SIMD PE engines would be implemented here and with some memory extension here. So everything would be very distributed with both locality, horizontal and vertical, so that we have a very scalable and modular architecture. We should have very reduced power consumption thanks to distributed computing. There will be no more global memory buffers. So that means that we do not need to store the global image in a global memory buffer and then process back and forth with weights and so on. Everything will be distributed into the architecture. We want to have and to achieve smart pixel support using industrial pixels for various applications, I said before, for both visible and infrared, and implementing in the ADC, in the cluster of the pixels, then dynamic range resolution, region of interest, wake up, and idle mode, local by part of the image. Of course, there is lots of architecture and application challenges, network sizing and mapping into this 3D distributed architecture, and what is going to be the hardware configurability that we are able to achieve versus the class of AI applications that we are achieving. So we are currently doing some high-level prototyping and sizing using in-house tools and high-level synthesis, HLS, in order to size the problem in terms of both memory sizing and memory and computation requirements. And we are also developing software mapping tools. Of course, then we'll have design challenges in terms of 3D physical design, because we have an heterogeneous system which is both analog and mixed signal, 3D place and route, testability, DFT, sign-off, etc. Now, going back to technology, in order to achieve such an architecture, we require to develop two new technology bricks, because if we have a 3-layer imager in terms of 3D stacking, we need to develop those two new technologies. So the first one is to be able to assemble 3 wafers using hybrid bonding, and this looks simple on the paper because this is only PowerPoint, but actually assembling 2 wafers, everybody knows that, but assembling 3 wafers and sealing the third one is not that easy. So we are working on that. And the second building blocks is high density TSVs, because we need TSVs in the middle die to be able to cross between the first layer to the third layer. And so we are developing some high density TSV with fine pitch, which is in line with the logic and memory tightly coupling that we are targeting in terms of parallel processing. So here are the current results in terms of technologies that we have today. So we have developed and designed some test structures with 3-layer wafers, die 1, die 2, and die 3. The pitch is between 500 nanometer and 1 micrometer with different test structure drawing. The wafer thickness of the middle wafer is 10 micrometer, and we have shown some different alignment analysis for the first step and the first interface, and the second step and second interface. So we are able at the end to achieve a misalignment in the range of 500 nanometer to 1 micrometer, depending on the layer. That proves that we should be able to achieve a pitch of 4 micrometer for both interface in terms of logic design rules. So these results have been published in more details at the MAM conference in 2020. And for the second technology bricks, so we are developing the high density TSV in the middle wafer. So this TSV is processed as a TSV-LIST process. That means that we are processing the TSV from the back face using the first wafer as a temporary wafer carrier. We are targeting, again, a very aggressive pitch for the TSV, 2 micrometer with a wafer thickness of 10 micrometer. We have currently first hybrid bonding flow that is able to achieve that with a TSV-LIST process with a nice morphological study. We have some nice cross sections, and we are currently doing some more characterization and process optimization. And here you can see some cross section of the high density TSV, where we can see this hybrid bonding interface, 2 micrometer pitch between TSVs and the line on the back face. Again, this has been published at the MRS communication in 2020 if you want to have more details. So to conclude the talk, again, to come back to the initial problems that we want to solve. So we are aiming to develop smart sensors and to develop smart image sensors as an edge AI device that is able to embed machine learning capability. In order to achieve that with a very low power and very reduced power budget within the device, we believe that we need a breakthrough in terms of architecture. And for that, we need to have a very tight integration of the computing within the sensor itself. And we strongly believe that if we are only able to integrate a standard computer vision or artificial network accelerator in the second layer or third layer, the benefits in terms of energy consumption will not be enough. So we need some disruptive technologies to achieve that. Hybrid bonding and high-density TSVs, we are preparing currently those technologies with pitches in the range of 2 micrometer and with CMOS technologies in 28 nanometer technology. This is a very good coupling in terms of logic density and TSV density in order to achieve the logic in the middle. And then in order to achieve that, we are currently designing this fully distributed pixel and computed architecture, integrating multi-scale, region of interest, wake-up, embedding neural networks. Of course, everything is heterogeneous with fine-grained 3D technologies. And to achieve this, of course, we need some SDTCO, so system design technology co-optimization and all the associated CAD tools methodologies. And we are working with our partners on that, on various topics to be able to achieve this in the coming period. So I would like to thank our partners through the IRT NanoElec program, and I will be pleased to answer your questions.
Thank you so much, Pascal. Very impressive talk. Thank you. Other questions?
Right. It's interesting that that there's no memory in the array that you're envisioning. So you're looking to be able to achieve good performance without having any memory integrated into the array. So I'll repeat the question. The question is, there's no memory in your array, so will you be able to achieve good performance without having memory in the array?
Yes, this is a good question. This is a good question. The main challenge is here in terms of memory capability, and we don't know yet. And we are currently sizing different applications in terms of what could be a good market of such a smart imager in terms of cost and area. And if we are able to fit the corresponding weights. Not the image, because the image would be distributed into the architecture using only SRAM, so we don't need large buffers, large enough to have enough frames, but fully distributed. But in terms of weight, we are currently sizing that. The second option in terms of to increase the density and not to go off chip, because if we are going off chip, of course, we are losing all what we are trying to do. Second good option would be non-volatile memory. And we have that in mind as well. So technology is not ready yet to integrate everything. On the paper, it looks kind of easy to integrate non-volatile memory in the middle of that, but technologies are not available yet. So today we are working without non-volatile memory.
Is there another question from the audience? So maybe I can ask you a question. So
yes, sure, Peter.
It's a three-wafer stacking process. This is really a big challenge. Also because if you look to the testability, no? So
yes.
In your concept, will you test the components on wafer level? And if there is a failed chip, do you stack then? Are you considering maps of the wafers or mapping to get a quite good yield, or how will you manage?
This is a very good question, Peter. I didn't mention that.
Sorry for that.
Sure. So to answer your question and to start from the beginning, so current images, BSI images, they don't do any test, and they do a blind assembly, and they test after the 3D assembly, after packaging actually, because they consider that the pixel processing, pixel wafer is very yieldable in terms of cost, And the only yield issues are on the logic wafer, which is one single wafer, and then the package and test afterwards. In our case, since we are going to stack 2 wafers using advanced technologies, we would like to test to stack not good die, because it wouldn't be non-good die. In that case, it would be not good wafers. So one of the solutions is to do correlation of maps between wafers and to stack the correct wafers with the correct wafers.
Interesting. Yeah. Thank you.
But simulation is also thought. This could be an option on longer term, because die-to-wafer and hybrid bonding technology is also technology that is currently developed for other kind of application, and it could be an option as well. It is not retained as a first solution, but that could be a second solution for more advanced technologies.
But then you may not have the 500 nanometer alignment accuracy.
No, so you can't have both.
That's true. So again, sorry for my questions, Ness.
Sure, that was a good question. No problem.
So if there are no other further questions?
Yes.
What was the pitch and size of the TSVs in the 10-micron thick part?
The question is, what was the pitch and size of the TSVs in the 10-micron thick part in the 3-layer process?
I'm sorry, I didn't get it. Paul, can you repeat that again?
What was the pitch and size of the TSVs in the 10-micron thick part?
The TSV pitch in that pitch is 2 micrometer and wafer thickness is 10 micrometer. Can you see the image?
Yes.
Yeah. So this is currently technology development and prototyping and characterization. So we are very glad of these very first results. And this is kind of reproducible. And we are doing characterization, electrical characterization, daisy chain characterization. We don't have all the results yet to present today. But if we are able to achieve a 2 micrometer pitch for face-to-face, face-to-bake, 3 assembly, and a pitch of 2 micro for TSV, we could have very aggressive logic coupling between the 2 layers, wafer 2 and wafer 3. So this is what we are targeting.
There's one comment in the chat. Is the TSV leakage small enough to be used to connect IR sensor? This was also before, sorry. Okay.
So is TSV leakage small enough to be used to connect infrared sensor?
Yeah.
I would say TSV leakage, there is no directly leakage. I mean, there is some resistivity. TSV resistivity is not very large, and this is such a small via. When we are achieving such object, there shouldn't be any issue. And with current BSI, they don't have any issue with TSV access. So I do not see issue there. And the other question is, perhaps I missed it, slide 20, about SI and PI findings, signal integrity and power integrity. So we are also working on not yet signal integrity, but power integrity and thermal integrity as well, in terms of early prototyping and system feasibility.
Okay. So, thank you, Pascal. Thanks again. Was a